Great. Thank you. Thank you very much. Thank you for inviting me. I'm very happy to give a talk in geometry and tacos. So today I'm going to talk about well, a problem that's very much related to some of the things we've seen in the last couple of days. In particular, there will be a lot of connections with Jean-Paul's talk and the talk with Erwan. But so somehow we will be adding some little extra piece of data to the problems we've seen, mainly to the scalar curvature equation. And this extra piece of data will be a B field, which yeah, I'm going to talk about in a minute. So everything I'm going to say is joint work with Jacopo Stoppa. Okay, so our general setting is that X will be some compact complex manifold of complex dimension n, and on this manifold we're going to be fixing a couple of cohomology classes. So first of all, we'll have a Kähler class, call it alpha, and then we'll have another class which so we're going to call it beta. It doesn't have any particular properties, just any cohomology class. And yeah, but just because we have fixed it from the beginning, I'm going to give it a special name. So usually I'm going to refer to this as the B field class. But yeah, it's just any random class. And so morally, the object I'm really interested in, rather than being alpha and beta, is more or less the complex combination in this way. But yeah, we still think about it as a pair of a Kähler class and some other cohomology class. So alpha plus I times beta, sometimes we will call this a complexified Kähler class. So it's a 1-1 class with complex coefficients. And yeah, where do these things come from? Well, they most often appear in problems related to mirror symmetry. So just a means of introduction, I'm going to be very briefly proposing you a way of seeing how these things appear in complex geometry and through mirror symmetry. But yeah, I won't be talking actually about mirror symmetry much. In fact, I'm not an expert at all, but it's just to give some motivation and a bit of context. And well, so first of all, some kind of very naive approach to mirror symmetry, if you will, could be stated like this. So you have two Calabi-Yau manifolds, and they share some kind of very deep property, and namely the moduli space of complex structure on the second manifold should somehow be in correspondence with the modular space of Kähler forms on the first manifold. And well, at least at the level of tangent spaces, these moduli of complex structures are parameterized by the H1 of the holomorphic tangent space of Y. So there should be like a T10. So this is a complex space. So essentially, the reason why these objects you might expect them to appear is that in this context, well, you would like to have a complex space also on the right-hand side. And so, yeah, morally, the correspondence between Y and X will be something like this. So, so in this way, we are naturally brought to consider this kind of complex valued classes. And we are still going to retain some positivity property for alpha. So at least the real part of the class will be positive. But yeah, so let me remark, however, that in the talk I will not focus on the case of Calabi-Yau manifolds, but this is sort of where these gadgets come from traditionally. So yeah, let's even go slightly deeper in this mirror symmetry theory to see what our main question will be today that we are trying to answer. So yeah, let me be slightly more technical for 1 minute. And so there is one version of mirror symmetry that's stated in terms of the Fukaya category of a Calabi-Yau manifold. So, but this is defined by the pair of the manifold together with a complexified Kähler form. So something of the shape Kähler form plus I times a B field, so an element of beta. And a choice of the scalar form is needed to describe this category. Well, for example, its objects are Lagrangians with some bundle and a connection. And so just the fact that they are Lagrangians tell you that they should have some connection with the choice of omega. And well, so on the mirror symmetry side, or especially in homological mirror symmetry, then you don't really care much about this because, well, if you make a different choice, then the derived categories will be the same. So it's not that big of a deal that you have to choose a complexified Kähler form. But somehow, if you want to extract some geometric information from this category, or rather, if you would like to find maybe some special elements of this big space, then you need to fix a complexified Kähler form in our complexified class. So the question that we are going to see today, and that hopefully I'm going to convince you that it's an interesting problem, is that well, we wonder how can we choose some representatives of this complexified Kähler class. So in other words, how can we fix more or less canonically the choice of a Kähler form in our class and a B field in our B field class. And yeah, so even though the motivation comes from Calabi-Yau's or maybe Fano manifolds, but the question makes sense completely in general. So we are going to be looking at this problem. And well, of course, this kind of question has been considered before. So and especially in some limiting regimes that are most interesting for physical applications, let's say. The way they usually fix a canonical representative of these two classes is the following. So assume you're in a Calabi-Yau, then, well, it makes perfect sense to ask your Kähler form to be Ricci flat. And this will fix then a choice of Kähler form. Now, once you've made this choice, then you can choose the B field as being the harmonic representative with respect to this Kähler form of its class beta. But somehow it's expected that if you are not close to this limiting regime, then you should have a different system of equations. And also, well, of course, this system per se doesn't make much sense if the manifold is not Calabi-Yau itself. Okay, so this is more or less the general picture. We are going to be looking for a system of partial differential equations that generalize this system here to less special cases. And just as a recap, maybe of some of the things we've seen in previous talks. Well, if we choose, for example, the class beta to be vanishing, then in this case, more or less, we are reduced to considering let's say, the classical Calabi problem. So you have a Kähler class, and you want to find a canonical representative of that class. And a possible answer, but in some sense, this is the correct answer, is that we would like to choose this representative as the solution of the constant scalar curvature equation. And well, some useful properties of this equation is that, well, of course, we know that solutions are unique up to automorphisms. And in general, the problem is obstructed. And to characterize the cases where there's no obstructions, somehow this has been the topic of a lot of research, I guess, for many years. But so by now we have some very interesting results, both from the algebraic side that we heard about, but also from the analytic side, such as the coerciveness of K energy, for example, is one of the main results, as was mentioned by I guess almost everyone in the previous days. So And also this equation allows you to build a modular space of some modular spaces of solutions, at least in some particular cases. So these are all very nice properties that we would like to have also for the equation that we're going to consider in our more general case when beta is different from 0. Okay. So an equation to fix a canonical representative of the complexified Kähler class was proposed by Schlitzer and Stoppa in around 2020. And the PDA looks like this. So I'm going to call this the scalar curvature equation with the B field. And as you can see, somehow is so it entails some non-trivial combinations of the Kähler form omega and the B field, and they are combined in a sort of slightly weird way. So I'm going to say a couple of words about how to read this equation. But notice that well, first of all, the equation depends on some coupling parameter, gamma, let's say, and if for some reason you put gamma equal to 0, then you will just obtain the constant scalar curvature equation. And similarly, if the B field is 0, then you're just going to obtain the constant scalar curvature equation again. So what are the things appearing in this expression? So first of all, you see here there's a complex combination of omega and B. So this is a 2 form, and when you take its determinant, it will be a top degree form. So you quotient it by your volume form omega to the n, and this then will be a complex function on your manifold. So essentially, we are then looking at prescribing the scalar curvature of the Kähler metric omega in such a way that the prescription also depends on omega itself. But well, you might notice there is a slight problem here. So the scalar curvature is a real function, and of course here instead we are looking at some complex function. So actually, if you take the real and imaginary part of this equation, you will find a system of equations. And I will rewrite this as a system slightly more explicitly in the next slide. But still, it's a system of equations, and actually also the coupling parameter is not really completely arbitrary. But the constant instead is completely fixed once you have fixed the two Kähler class. Sorry, the Kähler class, the other homology class beta, and this coupling parameter gamma. And this is just by integration. So if you integrate this against omega to the n, you will obtain just some topological quantities. And as I mentioned, the coupling parameter is actually not completely arbitrary. So at least its argument is uniquely determined by this condition. So again, if you take the integral of this expression against omega n, you will what you will find is that the real constant will cancel out the real parts, but for the imaginary part, we still have to get it equal to 0, and that's not a trivial condition. So, so the argument of gamma is uniquely chosen in such a way that if you multiply gamma by this complex number here, then we prescribe this to be equal to some positive real number. So notice in general, this might not be possible. So it might happen that if you take this integral of omega plus ib to the n, then you get 0. But we're sort of, well, assume that this does not happen. So we are only interested in the case when that does not happen, at least for now. Okay. So these are some sort of very elementary properties. But let's see how to rewrite this equation as a system, and maybe in a slightly more explicit way, so we can get a better feeling for what's going on. So to rewrite the equations, yeah, I'm going to call lambda1, lambda2 up to lambda n the eigenvalues of the two-form B with respect to omega. So if you like, take a system of normal Kähler coordinates. So in this system, then let's say at a specific point of P, then omega at that point will just be the standard symplectic form, while we can choose the coordinates so that also B becomes diagonal somehow. And these n eigenvalues will be real. Or another way to see this is that you're just diagonalizing an endomorphism of the tangent bundle of X. Okay, so with this notation in place, then you can sort of see that the determinant of this complex combination of two forms is actually just equal to, well, the determinant of omega, so your Kähler volume form. And then this gets multiplied by the product of all these complex numbers, 1 plus I times lambda A. This is just because we are taking omega plus I times B on the left-hand side. Okay, so essentially to rewrite the equation as a system of two equations, we'll just take the radius and argument of this complex number that's multiplying omega to the n. So this is the old equation that we started with, and yeah, so either you take real and imaginary parts, or you decompose this as angle times a phase, sorry, phase times a radius, and this is what happens. So the first equation is that the imaginary part of this thing should be 0. And the second equation is that the scalar curvature should equal the real part of this expression. But then again, in terms of the lambda A's, the system is just this thing. So we want the sum of the arguments of those complex numbers to be equal to the argument of gamma. And well, this is just fixed topologically, at least mod 2 pi. While the scalar curvature of omega instead should be equal to a constant plus this radius function. Okay, so this is the system of equations we are going to be talking about for the next few slides. And yeah, let me remark that the first equation here is actually something that's rather well known by now. It's called the deformed Hermitian Yang-Mills equation. So essentially, this equation that should be fixing a canonical way to choose omega and B. It's actually a coupling between the deformed Hermitian Yang-Mills problem and the constant scalar curvature problem. And yeah, so as I was saying, this equation has been studied a lot, but only in the case when you have fixed the Kähler form. While in our situation, instead, the Kähler form will be variable also. But just assume for the moment that that we know how to fix a Kähler form, and we just look at the deformed Hermitian Yang-Mills equation. But then the most interesting property for the problem, at least as I've stated it, is that it is somehow dual in the sense of mirror symmetry to the special Lagrangian equation. Again, if you are considering the case of Calabi-Yau's with some polarization. But most importantly for us, we have that solutions inside this class are unique if they exist. So it doesn't really depend on the choice of a Kähler form if a solution. Sorry, if you have fixed a Kähler form, then solutions actually are uniquely determined by this choice if they exist at all, but they might not exist in general. However, it's been known that at least in some regimes, the so-called critical phase regime, then the existence of solutions for the first equation then is equivalent to a stability condition. And in particular, this implies that the existence of solutions to the first equation doesn't really depend on the choice of Kähler form in the Kähler class, at least in some cases. So, well, this looks already quite good because we do have a condition that's tied to a stability some stability condition of X and the classes alpha and beta. And yeah, so, well, of course, having written the system, we know that at least in some cases, there is already a system of equations that's used to fix our canonical representatives. So we better check that in those situations, the two proposed things agree. And this is indeed what happens. So if we have two cohomology classes, and again, alpha will be the Kähler class, so it's positive, while beta essentially is a random cohomology class, then you can consider the rescaled complexified Kähler class given by multiplying alpha by some large positive number. And when you take when you sort of make kappa go to infinity, then this is what is usually called the large volume limit. So let's see what our equation becomes in this large volume limit. So essentially, let's plug kappa into all places and see what happens at least to the leading order terms of our system. And so, well, it's not very difficult to see that for the first equation, we'll get that the first non-trivial condition is that the sum of the eigenvalues should be equal to a constant, while for the second equation, we'll find that the scalar curvature should be equal to a constant. So if you, so the leading order terms are those multiplying k to the -1, by the way, and you find this system of equations. And now, if you play around a bit with the Kähler identities, you will realize the first equation is actually just asking of B to be the harmonic representative of its class. So in particular, if we are on a Calabi-Yau manifold, then we exactly recover the equations that are already considered in the literature. At least, in this sort of limiting regime. Okay. Also, if there's any questions at any point, feel free to interrupt. That's okay. So let's see some properties and maybe some even additional motivation as to why one might want to consider this equation. And well, so for Stoppa and Schlitzer, and frankly also for me and Jacopo, the main motivation for considering the system was that it's obtained through the formalism of moment maps, sort of similarly to what Rui described in the first talk. So we have that, we have that both conditions. So the deformed Hermitian Yang-Mills equation is a moment map for some action, while the Costa-scalar curvature equation is a moment map for a different group. And so the realization that these two groups actually fit into an exact sequence allows you to sort of see that there is actually kind of a natural Hamiltonian action of this extended group on a subset of the product between A and J. So, so this, by the way, tells you where the coupling parameter comes from. So essentially, the coupling parameter is telling you which of these two factors has more weight in the problem. So which of them is somehow more important, if you will. And yeah, so just to tell you very briefly what these actions are. So assume that the B field class is the first Chern class of some line bundle. Then the first action is will be just a gauge group action on the space of connections on this bundle. And yeah, so instead for the second one, we have the group of symplectromorphisms acting on complex structures of X, and they sort of quite naturally fit into an extension. So this is this property is kind of important, at least because it has many formal consequences. So first of all, there are some algebraic abstractions, such as Matsushima's criterion. Literally Matsushima's criterion, meaning that for solutions to exist, it's necessary for the automorphism group to be reductive. We have a Futaki-like invariant, something similar to the Futaki invariant. There's a variational characterization of the equations, and we can expect to have uniqueness of solutions, at least up to automorphisms, which are all very desirable properties that we set out to obtain, and indeed we are seeing more or less. But these are all formal consequences, so it's you still have to do some work to check that all these things actually hold true. And this is more or less what I've been working on. But still, at least this paints a very appealing picture for the problem we set out to solve. Okay. So I guess one useful thing would now be to have some examples of situations in which we can actually solve the equations, maybe some situations in which instead you can't solve the equations. And well, a first step in that direction is to look at the equations somehow, maybe modifying the parameters somewhat, and seeing if in some cases we can recover some previously known systems, some maybe some slight modifications of previously known equations, and things of that kind. And well, for example, the equation has radically different properties in the large volume limit. So if you take the deformed Hermitian Yang-Mills in the large volume limit, so you look at the leading term expansion of this equation, well, you find just some equation that you can always solve. But in the finite in the finite case, instead you might not be able to solve the equation. So, well, one way to look for examples could be to say, well, let's start from the large volume limit, and under which assumptions can I modify the solution that I get in the large volume limit to obtain a solution in some finite limit instead. So let's say for some finite value of k rather than for k infinitely large. And well, you can do this in the large volume limit, but in principle, you can rescale in many other directions. And just to show very briefly what happens, if you rescale both k and the coupling constant, you find a lot of different equations actually. So here on the upper left corner, this is just the large volume limit, so k is going to infinity, and instead we are letting the constant gamma times k to the -1 fall to 0, essentially. And this is just the large volume limit, so Well, of course, there might not be always solutions of the constant scalar curvature equation. So conjecturally, in the upper left corner, we have K stability, but we don't have any stability condition instead on the other class, beta. So on the lower left corner, instead, we have, again, the scalar curvature equation coupled with the J equation that I guess Zach is going to talk about in the next seminar. And yeah, on the upper right corner, we find a system that looks slightly weird, but it's always solvable. So it's more or less trivial. And on the lower right corner, instead, we find something that is very strange. So it's coupling the J equation with the Monge-Ampère equation. And my intuition is that this thing almost never has solutions. So one possibility then is to start in one of the corners where we might expect solutions to exist, then try to perturb a little bit to obtain existence of solutions for some examples, at least in the finite regime, so for the equation proper. And yeah, this is more or less the topic of this paper with Jacopo. So essentially, what I'm going to talk about in the last few slides is how to perform this strategy near the large volume limit for a very special choice of manifold. And yeah, okay. So I guess this could be a good point to ask any questions. Otherwise, just save them for the end. I don't know if there's any preference for that. Well, okay. So then let's look at an existence result. And well, as you will see, the result itself is quite special, but somehow it's yeah, I think it serves as a good example to highlight some of the properties one might expect when studying the existence of solutions for this system. So our setting now will be that of toric manifolds. Yeah, here I've written variety, but actually no, just a manifold of dimension 2 or 3. So in dimension 1, the system itself is completely trivial, just reduces to the scalar curvature equation on a Riemann surface. And we're going to make one very strong assumption that there is a CSCK metric in the class alpha. So let me go back one slide. So this tells you that we do have a solution for the system in the upper left corner, this diagram. So we assume that. And then what can we say? So there is a solution of the equation. Well, so to be more precise, I should say there is a solution of the extremal version of the equation. And this this existence will hold for any choice of a large volume class. So classes, oh, okay, sorry, this is a typo. So I've written beta plus I times k alpha, but it should be k alpha plus I times beta. So sorry for that. But anyway, for each choice of k very large, there will be a solution of the equation. At least if you assume a few other things. So well, this would be a very nice result to have, but it's not quite what we are able to get. So we have to assume that the starting class, the starting classes are already quite close together. So in particular, beta will be a positive class, so it could admit Kähler forms inside it. And also the coupling constant cannot be arbitrarily large. So for gamma equal to 0, we would just find the scalar curvature equation, and of course there is a solution for that one. But actually, it turns out that we can find a solution for every value of the coupling constant in a ball around the origin. And this ball has a radius that's possible to compute quite explicitly, depending on x, alpha, and the k that you're working with. And in particular, it will turn out that gamma times k to the -1 is positive. So in this picture, in the picture in the previous slide, there is actually a some positive interval, some positive open interval that's for which we can find solutions. So the statement as it is slightly vague, but yeah, the last two slides will be about sort of trying to give the idea of the proof, and hopefully that proof should in particular explain how large you can take this constant to be. And we do not claim to have an optimal value for the possible values of the constant. So, sorry, an optimal upper bound. So it might be possible for there to be solutions even for larger gammas than the ones we are going to find. Okay, so essentially the proof goes through a continuity method, as it's quite natural in this context. And the continuity method, the continuity part is just given by rescaling the coupling parameter. So for the coupling parameter equal to 0, we have the constant scalar curvature equation, which we are assuming to be able to solve. And then essentially you're asking, okay, how large can your t get? So up until which coupling constant, which value of the coupling constant you can actually prove openness and closedness along the continuity path. And just to make things simpler, I will try to explain how this works, especially how the estimates works in the case of surfaces, so in complex dimension 2. So one very special case of surfaces is that the scalar curvature equation with B field can be rewritten in a very nice way as a coupling of a Monge-Ampere equation together with a twisted constant scalar curvature equation. And in particular, yeah, so here the notation is just we've substituted theta for the argument of gamma. And if you play around with the expression, you can not too easily, but also it's not super difficult to end up with this kind of expression. So it's just a Monge-Ampere equation here that we will surely be able to solve, at least under our assumptions that imply this angle theta to be small and positive, and the class beta will also be a Kähler class. So you always have a solution of the first equation for each choice of Kähler form. So then, yeah, let's call beta of omega, B of omega, the solution of the first equation, and then you sort of plug it into the second equation, and you find some kind of twisted scalar curvature equation. Well, there is an important difference to the twisted CSK equation in that this B, so the B field will also depend on omega. So there aren't very many general results that can help you find a priori estimates for such a thing. Okay, so then let's assume we are just rescaling the coupling parameter. And at least, yeah, for the extremal version of the equation, it's relatively simple to get openness following the classical Lebrun-Simarka argument. And well, this is why you need to consider the extremal version of the equation in general, is that your Futaki invariant might not be 0, of course. So it's not really simple, but it's somehow you have a general way to establish this kind of result. But the most difficult part, so establishing the a priori estimates, is kind of complicated, and yeah, and actually this is the point in which we really need that the dimension is 2 or 3. But let's stick to the two-dimensional case, in which we have this much nicer expression for the equation itself. And okay, so the key point is that on the surface we have a very direct estimate for the quantity appearing here on the right-hand side of equation number 2. So if you assume that the first equation is solved, so you have a solution of this Monge-Ampère equation, and if you also assume that the B field realizing the solution is positive, as will be, then if you again play around with this expression of the eigenvalues of B, you will find that the sum of eigenvalues is always bounded above by the tangent of theta, which is a topological thing fixed from the beginning. So you have an upper bound for this function, the contraction of B by omega, and this upper bound doesn't depend either on omega nor on B. And having this, then it's not super hard to get the full a priori estimates. And yeah, so I noticed I'm maybe running out of time, so let me go through this slightly quickly. But the main point is that there is a theorem by Chen Li Sheng, and it's just been published, I guess, last month. That so if we are in the toric context, then they propose, sorry, they have a criterion that completely characterizes the existence of solutions of the prescribed scalar curvature equation in terms of a stability condition on the toric manifold, the Kähler class, and the function you are prescribing your scalar curvature to equal. And in particular, they show how this condition of toric uniform K-stability guarantees a priori estimates for solution of the prescribed curvature equation. And we can sort of follow their method to obtain the estimates we need. So, because we are assuming that x, alpha, and a constant is a toric uniformly K-stable, since, well, we are assuming there to be a constant scalar curvature metric in alpha. And this toric uniform K-stability is an open condition. So, well, it's an open in the sense that if you have a bound on the function that you are trying to reach with your scalar curvature, then you can sort of find explicitly how big this factor gamma can be to retain this property of toric uniform K-stability for this triple. And so more or less from their strategy, you get a priori estimates. And let me mention that this theorem by the three of them is essentially a corollary. Well, of course, you have to do some work, but it's a corollary of Chen Cheng's estimates. So this is why it really works. So secretly, we are using their estimates. Okay, then I guess my time is up, so we'll just leave you with 3 questions on the last slide, and thank you for the attention.
Thank you for the talk.